Okay, so today we're going to talk about strong induction, which is somewhere in the midst of 4.2 in your textbook. We'll also talk about sequences, which is somewhere also in this 4.2, 4.3 area, but I'll probably just call this chapter 4, part D. Next time, we're going to do some more graph theory, which will involve some more induction. And then after that, we'll move on to chapter 5. And then I think I'm actually going to go back to the numbering of the book. Okay. So I won't tell you yet what strong induction is, because actually let's motivate it by looking at a problem where we'll actually need to do something slightly different from induction, something that seems a bit stronger. And then we'll talk about what the principle of strong induction is. Okay, but in order to do this, let me first define what a sequence is. So a sequence is an infinite list of numbers that is indexed by an infinite subset of the natural numbers. So we often write a sequence in the form A1, A2, A3, right? The number AN is called the nth term in the sequence. So like in calculus, you learned about sequences and series, right? Sequences were just infinite lists of real numbers. Series were like where you had to sum them up, right? I will say that sometimes people use the word sequence even if the list is not infinite, but it's not so important. So you could just say that a sequence is a list of numbers that are indexed by the natural numbers. But let's just say that sequences will be infinite for us. Okay, also here you'll notice that I think it's more natural to start sequences sometimes with A0 and sometimes with A1. So here, when I say n, I mean sometimes it includes 0, sometimes not. So some sequences, it'll be convenient to start at A0 and then say A1, A2, A3 is just a more natural numbering system. For some sequences, it's more natural to start at A1. Whether the natural numbers include 0 or not is basically like only a technical point. It's not really all that important. Okay, so there's lots of sequences, right? Maybe the first sequence is just 1, 2, 3, 4, 5, 6, where the nth term in the sequence is just n. Right, that's a sequence. Or another nice sequence, 1, 1/2, 1/3, 1/4, 1/5. Right? Or maybe 1, 1/2, 1/4, 1/8, 1/16, where the nth term in the sequence is 1 over 2 to the n. Right here, maybe it'd be nice to say that an equals 1 over 2 to the n, in which case this would actually be the A0 term. This would be the A1 term. This would be the A2 term. Right, so the first two sequences, it's convenient to index starting at 1. The third one, maybe it's most convenient to index starting at 0. It doesn't really make so much difference. Okay, we can also define sequences recursively. Okay, so recursive like means something that refers back to a previous step, roughly. So maybe the most famous recursively defined sequence is the Fibonacci sequence. So define the Fibonacci sequence. Fn as follows. We'll let f0 be 1, f1 be 1, and for n greater than or equal to 2, I'll let Fn be equal to Fn minus 1 plus Fn minus 2. Okay, so what am I saying? I'm saying the first two terms of my sequence are 1 and 1. And then after that, the next term is you add up the previous two terms. And one of the most famous sequences in mathematics. So 1, 1, those are the first two terms. The F2 term is, you sum up these two, so you get 2. The next term is 1 plus 2, that's 3. The next term is 2 plus 3, that's 5. Next term is 3 plus 5, that's 8, 13, 21, 34. This is the famous Fibonacci sequence. So this is a perfectly good way to define the sequence because it tells you unambiguously what the next term in the sequence is. Okay. You could actually also come up with a closed form solution to the Fibonacci sequence, but let's not get into that today. Oops. Okay, I'll use that page later. So now let me ask you a question. Here's the question. How many ways can you tile a 2 by n grid with dominoes? Okay, so maybe you have no idea what I'm saying by this. So let's say 2 by n grid, right? So a 2 by n grid, the first, just like in linear algebra, the first number generally refers to the number of rows. So this is a grid with 2 rows and n columns. So let me just draw several here, right? So a 2 by 1 grid. A 2 by 1 grid looks like this. The 2 by 2 grid looks like this. The 2 by 3 grid looks like this. 2 by 4, etc. That's what a 2 by n grid is. And what do I mean by tiling a grid with dominoes? Okay, well, maybe you know, maybe you don't know that a domino is like a 2 by 1 rectangle, right? And if you're playing the game dominoes, there's like some certain number of dots on each side of the domino, right? So domino is a 2 by 1 rectangle. Oh my gosh, I hate when this happens with OneNote. Is a 2 by 1 rectangle. And to tile the grid means to cover every square of the grid once and only once by using dominoes. Right? So this first grid, this 2 by 1 grid, I can just place a domino. Maybe I could try to do something fancy here. No. OneNote won't let me. OneNote won't even let me change pens at the moment. Wow, this is bad. Oh man. Okay, now it'll let me change pens. Okay, so you can just place one domino across the 2 by 1 grid. Right, we could also tile this 2 by 2 grid by putting a domino there and a domino there. For this 2 by 3 grid, I could place a domino here, and a domino going down this way. Of course, these are not the only ways to tile these grids. Right, so for the 2 by 2 grid, instead of using 2 horizontal dominoes, I could use 2 vertical dominoes. That would also tile the grid. So a tiling of a grid by dominoes is covering every square exactly once by just using dominoes, which means that you have to cover 2 adjacent squares. So the question is, how many ways can this be done? Well, let's see. This is n equals 1, n equals 2, n equals 3, n equals 4. There's an n equals 5 case. Maybe just be clever, let's have an n equals 0 case over here. So the empty grid with no dominoes in it. And let's try to figure out how many ways there are to tile these grids with dominoes. Okay, so actually, I'm going to again ask you to pause this video and figure out how many ways you can tile these grids with dominoes. Let me give you the first answer. This n equals 1 case, there's only one way to tile that with a domino. You just have to cover both of them with a single domino. The n equals 2 case, there's two ways. You can use either horizontal dominoes or vertical dominoes. Now I want you to figure out at least up to n equals 5, just to try to understand what's happening. Okay, so I trust that you did that. So for the n equals 3 case, we could do the way that I pictured, or we could flip it horizontally, right? So actually, let me just try to enumerate them like this. So there's the pictured way. We could also flip it horizontally. So put one domino here, one domino here, one domino here. We could also do 3 vertical dominoes. That's also allowed. But that's actually it, right? I can even give a little proof of this fact, right? If you look at this upper left-hand square, right? If you look at this upper left-hand square, it's either covered by a horizontal domino or a vertical domino. If it's covered by a horizontal domino, then that means that this bottom right-hand square is also covered by a horizontal domino because there's no room for a vertical domino. So that completely determines the tiling. That's the first tiling we came up with. On the other hand, if the upper left-hand corner is tiled by a vertical domino, then now we just need to look at what's left, and there's two ways to tile this, right? There's with 2 horizontals or with 2 verticals. And those are exactly the 3 ways that we came up with. So in enumerating all the possibilities, you can actually show that these are all of the possible ways. So there's 3 ways here. What about for 4? So let's try to do this, right? So I could do all horizontal dominoes. There's 1. I could do the first 2 horizontal dominoes, then these ones vertical. That's 2. I could go vertical here, then horizontal, horizontal, vertical. That's 3. I could go vertical, vertical, horizontal, horizontal. That's 4. Or I could go vertical, 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 vertical. That's 5. So there are 5 ways here. Okay, notice I left out the n equals 0 case. How many ways are there to tile the 2x0 grid with dominoes? You might be tempted to say 0, but I think a mathematician would be much more likely to say that there's one way to tile it, which is not doing anything, is tiling it. Why is this a better answer than 0? Because there's a big difference between, say, a 2x0 grid, right? This is a 2x0 grid, versus like, say, a 3x1 grid. Right? A 3x1 grid, there's just actually no way to tile this with dominoes. So this one would have 0 ways. But a 2x0 grid, technically we've already tiled it with dominoes. So that would be one way. Okay, and then n equals 5, maybe you could try to figure out, but I'll tell you the answer is 8. So now, do we have any conjectures, once we have this much data, about how many ways there are to tile a 2x(n) grid with dominoes? Hopefully, you're realizing that this thing that I did on the last page was not by accident. What I have is 1, 1, 2, 3, 5, 8. This looks like the start of the Fibonacci sequence. So this can be a conjecture. The number of ways, let's say for any natural number n, the number of ways to tile a 2x(n) grid with dominoes is the nth Fibonacci number, Fn. Okay, and this, I think, is an insight that we could only gain by doing some experimentation and some exploration. I would say that before we actually started looking at how many ways you could tile these with dominoes in the small cases, there's sort of no guess as to what the answer should be. Right? So how many ways can you tile a 2x100 grid with dominoes? I have no idea. But once we did some experimentation, we noticed that, oh, there's maybe some kind of pattern happening here. We can come up with a conjecture. Now that we have a conjecture, we can try to prove it. Okay, how do we prove such a thing, though? To figure out how to prove something could also require some insights, right? So coming up with this conjecture required some experimentation and some insight. Trying to prove it will also require some insight. Okay, well, the thing with Fibonacci numbers is that they sort of naturally depend on the prior cases, the prior two cases. So since they depend on prior cases, something like induction might be helpful because, right, in an induction proof, it's like you assume something is true for k, you prove it for k plus 1. It's like you're relying on a prior case to understand the next case. That's sort of how the Fibonacci numbers work. However, it's not exactly going to work. I mean, it seems like that's actually not quite what we want, because the thing with an induction proof is that in an induction proof, you only assume something about the previous case. But Fibonacci numbers depend on the two previous cases. Right? So how to prove? So induction, maybe, but Fn, let's say Fk plus 1 depends on both Fk and Fk minus 1. So like this statement that the nth Fibonacci number is the number of ways to tile a 2x(n) grid, we could call this whole statement P of n. And what I'm saying is that to understand P of k plus 1, it depends on both P of k and P of k minus 1, which is not something that we were set up to do with induction. Okay, also, for the base cases, so if P of k plus 1 depends on both P of k and P of k minus 1, that means in order to understand F2, I need to know both F0 and F1, right? If I understand F0 and F1, I understand F2. If I understand F1 and F2, I understand F3. If I understand F2 and F3, I understand F4. So one thing that's maybe kind of clear is that we'll need two base cases as well in order to try to use an induction argument. Okay, but I will try to prove this with induction, which technically I can't do, but we'll modify our technique right afterward so that we can do it by some kind of induction. Okay, so let's prove this conjecture by induction. So proof of conjecture. So we prove this by induction. Okay, I put an asterisk in your notes though, because it's not induction yet. I mean, technically it's not induction, but we'll know what it's really called in a second. Okay, so for the base case, I actually need two base cases, right? In order to start off, in order to understand the second Fibonacci number, I need to know the 0th one and the first one. So we have two base cases. Okay, so when n equals 0, there's only one way to tile the empty grid, which is just do nothing at all. And also F0 equals 1. So it's true that this statement is true when n equals 0. The number of ways to tile the 2x0 grid is the 0th Fibonacci number F0. Okay, when n equals 1, there is one way to tile the 2x1 grid, right? Namely, you just place a single domino here, right? And the first Fibonacci number F1 is 1, so the statement holds for n equals 1. Right, so you just simply cover it with domino. That's the only way to do it. Now, the inductive step. Okay, so I said that to understand the kth Fibonacci number, or the k plus first Fibonacci number, you need to know the previous two ways. So in the inductive step here, what I'll do is I'll assume, let's assume that the number of ways to tile a 2 by k minus 1 grid is fk minus 1, and the number of ways to tile a 2 by k grid is fk. So in my inductive hypothesis, I'm assuming a bit more. Now I want to understand the number of ways to tile a 2 by k plus 1 grid. So let's suppose we have a 2 by k plus 1 grid. Right, so we have some ... here, and then the grid finishes like this. So this is a 2 by k plus 1 grid. How many ways can we possibly tile this? Well, if we go back to the insight we had in the 2 by 3 case, one thing we could do is we could just look at the top left square of the grid. So think about this square here. There are two cases, right? That one's either covered by a horizontal domino or it's covered by a vertical domino. So the top left square. So let's say in any tiling, the top left square is covered by either a horizontal domino or a vertical domino, but of course not both. Right, in a tiling, every square has to be covered exactly once. Okay, well, if it's covered by a horizontal domino, then this bottom left square also has to be covered by a horizontal domino because there's no room for a vertical domino. So if we place a horizontal domino there, what are we left with? We're left with tiling a 2 by k minus 1 sized grid. And how many ways are there to do that? Well, by assumption, that's fk minus 1. On the other hand, if this top left square is covered by a vertical domino, then what's left over is a 2 by k grid. And by the induction hypothesis, the number of ways to tile that is fk. Therefore, I have how many ways to tile? Well, if I use a horizontal one, I have fk minus 1. If I use a vertical one, I have fk. Add those together, that's all the tilings of this 2 by k plus 1 grid. And that's exactly f sub k plus 1. Okay, so let's just finish writing this proof. So if the top left square is covered by a horizontal domino, then so is the bottom left square, because there's no room for, right? Again, the picture is like this, ... If there's a domino here, then there's no choice but to put a domino here. What remains is a 2 by k minus 1 grid. So the number of tilings in this case, right, is f sub k minus 1 by the induction hypothesis. All of the tilings that start like this are just two horizontal dominoes followed by a tiling of the remaining grid, and there's fk minus 1 ways to do that. On the other hand, if the top left square is covered by a vertical domino, and so now the picture is like this. Well, then what's left over is just a 2 by k grid. So the number of tilings like this is fk. Okay, so really here what I've done is I've broken into cases. So really maybe I should say case 1 and case 2. That way my reader knows, oh, there's only two possibilities. The top left square is covered by the horizontal, or the top left square is covered by a vertical. And that's all the cases, because the top left square has to be covered by some domino. So hence, the total number of tilings of this 2 by k plus 1 grid is fk minus 1 plus fk, which is exactly equal to fk plus 1 by the definition of the Fibonacci sequence. So by induction, asterisk, we have shown that the number of tilings of a 2 by n grid is the nth Fibonacci number Fn. Okay, so kind of a clever little proof. Okay, but like I said, technically this proof does not follow from the principle of mathematical induction that we learned, because the principle of mathematical induction that we learned said, if you can prove the first case, and you can prove that the kth case implies the k plus first case, then you've proven all the cases. What have we proven? We've proven that we can show the first two cases, and then we've proven that if you know the first and the second case, it proves the third. If you know the second and the third case, it proves the fourth. If you know the third and the fourth case, it proves the fifth, etc. But that sure does seem like enough, right? That's like saying, I will knock over the first two dominoes, and I'll prove that the first and second domino knock over the third, so therefore the third one falls over. And I'll prove that the second and third domino knock down the fourth, but since the second and third domino have fallen over, then the fourth one is knocked over. And I'll prove that the fourth and fifth one the third and the fourth one knock down the fifth. It seems like if you could prove that, then it still proves that all the dominoes fall over. So what we'll do is we'll learn a slightly different technique, which is sometimes called strong induction. It's sometimes called complete induction. And your book calls it the second principle of mathematical induction, but I prefer strong induction or complete induction. So what I'll call it is I'll call it the principle of strong mathematical induction. So that's this technique. It's a strong mathematical induction. So what is this technique? So for your inductive hypothesis, in the inductive step, instead of assuming the statement is true for the previous case, right? So instead of just assuming that P of K is true, assume it is true for all smaller cases. So you assume that P1, P2, up through Pk is true. And then you prove that P of K plus 1 is true. Okay, also we saw that you need to alter the number of base cases potentially. So the number of base cases depends on how many of the cases you use in the inductive step. Okay, so I'm being a little bit vague because it depends from proof to proof. Okay, so in terms of dominoes, what am I doing here? In terms of dominoes, what I'm proving in the inductive step is that if all of the first k dominoes fall over, then the k plus what first domino falls over. I'm proving that if you know that all of the first k dominoes fall over, then the k plus one first one falls. So if you knock over the first domino, so sometimes there can be just one base case still, but if you knock over the first domino, then all of the first one dominoes fell over, which means that you know that knocks over the second. But now since you know that the first and the second are knocked over, that shows that the third domino falls. And since you know that the first, second, and the first three dominoes all fall over, it knocks over the fourth, etc. So if you can prove this inductive step, and you do the correct number of base cases, which depends on your inductive step, then you can prove that the thing holds for all n. Okay, and this is called strong mathematical induction because it seems stronger than the principle of mathematical induction, because we're doing almost exactly the same thing, except in the inductive step, we're allowed to assume way more. Instead of just assuming P of k, you assume all of the statements up to k. So it seems like it's stronger than regular induction, but it turns out that actually they're equally strong. It turns out that they're actually logically equivalent. You can prove that if strong mathematical induction is true, then mathematical induction is true. And if mathematical induction is true, then strong mathematical induction is true. And actually, both of these are equivalent to the well-ordering principle for subsets of positive integers. But that's a really technical subject. Okay. The thing to know for you is that sometimes in a proof, you'll need to know more than just the previous case, in which case technically you're doing a strong induction. Okay, so I think I owe you another example before I have you go prove some things on homeworks. So let me give you one more example where we actually need to use the power of strong induction. So here's the theorem. Every positive integer n greater than or equal to 2 can be written as a product of prime numbers. Hopefully this theorem is familiar to you. This theorem says that every positive integer has a prime factorization, right? So you already know that like the prime numbers are like the elements, right? In chemistry, right? Every molecule is built out of elements. Every integer you can write as a product of primes. They're like the elements multiplicatively that make up every integer. And we'll prove this by strong induction, and we'll sort of see why when I present the proof. Okay, so here's the base case. Here's the proof. We will prove this by strong induction. Okay, so it turns out in this case, we'll only need one base case, but we'll actually only realize that we only need one base case after we've done the inductive step. So the thing with a strong induction is that the number of base cases you need depends on how you prove the inductive step. But like just in general in mathematics, you oftentimes don't know what you need to do until you've done it. So in fact, it's not even clear if you're starting a proof that seems like it'll be an inductive proof. Sometimes it's not clear whether you'll need induction or strong induction. But in the middle of your inductive step, you'll realize, oh, I need more than just the previous case. I need all the cases smaller. And then you need to go back up and adjust adjust your proof to say, oh, well, it's by strong induction. Or in the middle of your inductive step, you'll realize, oh, I need more base cases. But since I get to present it from the beginning to the end, I know that there will only need one base case. So for the base case, when n equals 2, since 2 is prime, it is the product of 1 prime. Two equals 2. So every prime number you can write as just itself, which is a product consisting of a single factor. Okay, now for the inductive step. So in a strong induction, in the inductive step, you suppose that for some k greater than 2, every integer 2, 3, 4, up through k can be written as a product of primes. So in our inductive hypothesis, we get to assume a lot more, right? If this were a regular induction, I would only be able to assume that k itself could be written as the product of primes. Okay, so we want to show that k plus 1 can be written as a product of primes. Okay, there are two cases. Right, so case 1, if k plus 1 is itself prime, we're done. Because you can just write it as itself. It's already written as a product of primes. Right. Case 2, if k plus 1 is not prime, what does that mean? Well, we said that to say that a number is prime means that it cannot be written as a product of two strictly smaller integers. Which means that if it's not prime, it is possible to write k plus 1 equals m times n, where m and n are integers, and they're strictly between 1 and k plus 1. We can actually write it as a product of two smaller things. Another way to say that they're between 1 and k plus 1, though, is to say that they're between 2 and k inclusive. So I don't know how to do this exactly, but if k plus 1 is not prime, then there's definitely some way to do this for some m and some n. But now the good thing is that by the inductive hypothesis, m and n can both be written as the product of primes. Okay. So by the inductive hypothesis, m and n can both be written as the product of primes. Let's say m equals p1 times p2 up through pr, and n equals q1, q2 up through qs, where r and s are natural numbers, and pi and qi are prime. So I don't know how many primes, but I do know that you can write m and n both as a product of primes, right? But then k plus 1 is m times n, which is p1 up through pr times q1 up through qs, which means that I've written k plus 1 as a product of primes. Which means that by strong induction, every integer n greater than or equal to can be written as the product of primes. Okay, so this was a case where in trying to understand the k plus first step, in trying to understand the factorization of k plus 1, actually understanding just the previous case is actually no help at all. If you know how k can be factored, it tells you nothing about the factorization of k plus 1. But if you know that every smaller number can be factored into a product of primes, then if it's not prime, you break it up into two smaller numbers, and then those you can write as a product of primes. So here we needed the strength of strong induction. There's no way to prove this with just a regular induction. Okay, now notice also in this case, like in my inductive step, I never needed to know. I mean, this inductive step works even after just a single base case, right? So the way to think about this is to think about if your proof works as you just increment by 1 from the base case, right? So the base case was n equals 2. Now, does this proof help me for n equals 3? Well, yes, n equals 3 is prime, so we're done. Okay, what about 4? Well, 4 can be written as 2 times 2, and 2 was covered in the base case. So at no point as you're incrementing up did you need more than just the single base case 2. If we go back to this proof, this tiling proof, let's say you only did one base case. Let's say you only did f1 equals 1. I mean, the 2x1 grid. Let's say you only did the 2x1 grid. Well, in going from the 2x1 grid to the 2x2 grid, okay, actually, let's say like this. So let's suppose you knew just the, okay, so in going from the 2x1 grid to the 2x2 grid, you needed to know how many ways to tile the leftover, right? So if you know the 2x1 grid, there's only one way to do this. Then when you go to the 2x2 grid, the inductive step was like, okay, well, you consider this one. If it's covered by a vertical domino, that's covered by the previous case. If it's covered by a horizontal domino, you still need to know how many ways there are to tile the rest of it, which is nothing. This may be a bit confusing, but if you were going to the 2x3 grid, I mean, essentially, you already know that there's only one way that starts like this, because there's only one way period that is like this. So you are definitely using the fact that if you have no squares in your grid, that counts as a tiling. Okay. I'm probably being like a little bit confusing here. Using to think about whether your proof works with the number of base cases that you did. So this product of primes proof works. The induction gets started and keeps going just by doing a single base case. This tiling proof, you really need to know the two previous cases. And so to get to this third case, you need to know the second and the first case. So you need to do two base cases. So it depends on how your proof goes. There's no way to know at the start how many base cases you'll need. But that's when you'll just go back and edit your base cases to add another one if you need it, or to add two if you need it. Okay, so you'll get some strong induction problems on your homework. I don't actually remember whether I specifically say to prove by strong induction or not. Sometimes I'll just say prove this thing and you need to figure out how to prove it. So you might start by trying an induction, but then realize you actually need strong induction. One good question that you maybe would want to ask me is, why don't we just always do strong induction? Because strong induction seems stronger than regular induction, even though it's equivalent, because you just get to assume more in the inductive step. So why don't you just always do strong induction? So the answer is you could always do strong induction, actually. But if you remember back to that article I had you read for problem set 2, when you're presenting a mathematical idea, you should always assume as little as possible, because you don't want to give your reader a red herring. If you do something by strong induction, it's like telling your reader, oh, I'm going to need a bunch of cases in the inductive step, like a bunch of previous cases, not just the immediately previous one. If you only need the immediately previous one, it's much, much clearer if you do a regular induction. So in this class, if all you need is the previous case, I will say you have to do a regular induction. You can't do a strong induction. You can't just always do a strong induction, because strong induction proofs are a little bit less clear than regular induction proofs if regular induction suffices, because you're assuming more, it sort of clutters it up. Okay, so you'll get more problems on induction, strong induction. Also, like I said, next time we'll do some more graph theory, because several of you, I think, found that graph theory digression last time enjoyable. So we'll discuss a couple of nice induction proofs for graphs next time. And then after that, we'll move into chapter 5.